This is simple op-amp circuits with capacitors and inductors. So let's take this one. Let's take this circuit. So let's put a source here, we'll call it VS. Let's put a resistor called R sub S, the source resistor. And on the top, let's put a capacitor instead of a resistor now. In the question, what's V out? Going back to op-amp. The assumption we made, which is what? No current enters or leaves that node, right? So the current going in here is 0. The current coming out of this is 0. That's the first assumption. The other assumption that the voltage of the plus end and the minus are the same. What's the voltage right here? 0. So what's that voltage? 0. Let's assign current any direction that you want to. We'll call this I sub S or I sub R through the resistor. We'll call this current I sub C. Doesn't matter what direction. KCL at this node, it says what? If you take all the current entering that node, should equal all the current leaving that node. What's going to it, I sub R, and what's leaving, I sub C. Well, what is I sub R? I sub R is this voltage minus this one divided by that resistor. Vs minus 0 over R sub S. What's leaving that? 0 minus V out. We don't know what that resistor. So I can't use that. So then what are we going to do? Wait a minute. We know I equals what? C dV dt. So I label the current going that direction. So the value of that is going to be C, the derivative of the voltage cross. Since I'm going that direction, it's this voltage minus that voltage. Clean it a little bit there. And this will be negative actually. I can factor the C out, or is outside. Leave it out. Factor the minus sign outside. And I'm looking for V out. That's what I'm looking for. So to cancel, to solve for V out, I need to integrate this with respect to dt. Well, R is a constant, so it's 1 over R, V of S dt equals negative C, the integral of dV out. And what's the integral of dV out? Isn't that V out? This will be 1 over R, the integral Vs dt. Can you solve for V out? It's negative 1 over RC, the integral of Vs as a function of time dt. Now remember, this is not a DC, well, it could be a DC value even. Yeah. But the integral of that. And when you integrate, you're really going from negative infinity to where? To t, or t0, or t0, whatever you want to call it, to t. If you don't like to go to t there from negative infinity, you can break it down. So here we go, v out equals negative 1 over r sub c, the integral from negative infinity to t. You know, in calculus, if you have an integral like this, you can break it down from negative infinity to 0 plus from where? From 0 to t. Leave this one there. And this minus sign in the front is going to make it minus the voltage across the capacitor as 0. If they don't have the minus, it will be a plus, because that minus sign is going to make it minus. So minus the voltage across the capacitor at 0. And that's your voltage as a function of time. So notice this circuit now integrates the source. Integrates the source. That's an integrator. So if you want to build a circuit that will take the integral of a function, you want to put a capacitor there. Now you can actually adjust C and R by making the product equals to 1. You can make C equals 1 micro, right? If you make C equals 1 micro, and R equals 1 meg. A meg is a million, yep. 10 to the 6. This is 10 to the minus 6. What will happen here? What's V out as a function of time? This becomes a 1. And if this was not connected till I walked into the lab, which is my time equals to 0, that means there was no voltage there. When I walk into the lab, I connect that, that piece will disappear. So that becomes an integrator, except your output is going to be flipped a sign. What do you do to flip that sign? You take another op amp and you reverse them. Notice if I cascade this to another op amp here, put equal values right there on the top and here, that will give me the minus 1 on the top, and that will change it to a plus integral of that. So this type of a circuit, again, is called an integrator, because this will take the integral of the function that you're putting in.
But we would need equal values for the capacitors for the cascaded op.
To be equal to 1. If you just want to get the integral of that, unless you want to increase the signal or decrease it, you know. So if you don't want to change it, just want to take the derivative, then you want to make sure R and C are equal. But if you want to make it smaller or bigger, you adjust R and C such that this value is either bigger or smaller. Yeah. Now what about if I make a minor change to that? If I put the capacitor first, put the capacitor here, same circuit. Just flip the capacitor and the resistor. Would that change anything? Well, let's see. Same rule applies here. This is 0. This is 0. The voltage here is 0. The voltage here is 0. We'll call this current I sub C. We'll call this current I sub R. The current in KCL, the current going into the node, is equal to the current leaving that node. What is going? I can't use this voltage minus that over the resistor. I don't know what the resistor, I equals what? C dVc dt. So, and since I'm defining the current going this direction, it's Vs minus 0. It's this voltage minus that voltage, because I want it to be plus to minus if you're going to the right. So it's Vs minus 0 equals 0 minus, this is V out here, if you multiply both sides by R, what is V out equal to? Negative R times C, the derivative. So this will differentiate. Again, if we make R times C equals to 1, you have V out equals negative. So now the function will take the derivative and flip the signal. So this is a differentiator instead of a derivative. Again, if you don't like that minus sign, then you take another op amp here. You put 10K, for example, any value you want to put there. You put 10K here, and guess what V out now here? This becomes a plus. I'll call it V out bar. So V out bar will be positive dVs dt. So if you want to flip that sign, you just add to it this one, and the result of this, it's negative this divided by this times that value. So that's going to take it and just flip the sign for you.
The resistor doesn't matter what.
Doesn't matter what the value, any value, equal values here. R and R, you know. 10K, 10K, 2K, 2K, 5K, 5K, as long as they equal. So this is a differentiator. Yeah. And you can take the derivative of any function. You want to increase the value, decrease it, then you would play with R and C here. Shut up. I'm silent. I should, because I grabbed it so that doesn't make anything. Now, if you put an inductor, it changes a little bit. One more example here on these with inductors, because I said we'll do inductors. What about if you do an inductor on the top instead of a capacitor?
Wouldn't it just be like the opposite?
Well, let's see. Let's say this is L, and this is V out. Again, this voltage the same as this, 0, 0. Let's assign this current, we'll call it IR. Now I'm going to change this. I'm going to make the current go this way. No reason. I always make it go into the right, so I decided to change it. Really, I don't have any reason why I switch it. KCL of this node, if you take all the current going to that node, add them, it should equal all the current leaving. What is going to that node? Vs minus 0 over R plus, we know V equals what? L di dt. Remember that? Which means I equals 1 over L, the integral of V dt. So if you want that current, that's 1 over L, the integral of what? V, what's the voltage? It's V out minus 0 dt. From negative infinity to t. Clean this a little bit. multiply by L and move this to that side, I'll have if you multiply by L equals negative L over R times Vs. I want to solve for V out. How would I get rid of that integral? Yep, take the derivative both sides, because they are the inverse of each other. So we take the derivative of the integral, they cancel each other out, and you have V out as a function of time. It's negative L over R, that's a constant. What's the derivative Vs? dVs dt. That's also a differentiator. We'll take the derivative for you. And again, you can make L and R matching to make it equal to 1. If you can manage to make it equal to 1, usually the value of the inductor is really small. It's tough to make it a 1. You'll need a massive inductor to make that ratio go to 1. But V out is negative L over R dVs dt. So if this value is negative 100, for example, or 1/100th of the value, you can put another one cascaded to this where the value is 100th of that with the minus sign, and that will make it back to normal. Okay, what about a circuit that does not have op amps in it, just capacitors and inductors?
Oh wait, did you already say what happens if you flip the, I'm guessing it's the integrator?
Well, you can flip that, and you'll see that, actually. Put the inductor here,
Yeah.
the resistor there. You end up with reverse. Yeah.